Good afternoon, everyone, and welcome to Thermo Shorts. So we've been talking about how to fix states, and we've been focusing mostly on water, because water is this element that exists near the vapor dome in normal circumstances, because we can have liquid water over here, we can have water as water vapor, so steam, or some combination of saturated vapor and liquid. And we started to talk about how to look these things up in the table, and then we said, well, if it's liquid water, maybe there's some strategies we can use to avoid using a table. So now we're going to say if we're above the vapor dome but to the right of the critical point, where we'd have superheated vapor, do we always need a table here? And the answer is usually yes. But if we're talking about something like an ideal gas, it's going to be so far away from the vapor dome that maybe we can get away with not using a table in that case too. So in order to think about this, we want to talk about ideal gases. Now, ideal gases, we can think about them first by looking at this thing called a compressibility chart. Now, this is called a compressibility chart because on the y-axis, we have this thing called the compressibility factor, Z. So this is the pressure times the specific volume divided by what we're calling the specific gas constant, which changes depending on the gas, and multiplied by temperature there in the denominator too. Now, there's two variables here that are important for us. So one is the reduced pressure. That's the pressure divided by the critical pressure. And the other is the reduced temperature, which is the temperature divided by the critical temperature. Now remember, the critical temperature and the critical pressure are things that are defined by the tip of that vapor dome. So that's the highest temperatures and pressures where you can have liquid and vapor coexisting at equilibrium. So what does this graph tell us? Well, it tells us that we can use the ideal gas law, which is just setting this equation, Z equal to 1, that happens on this graph in particular cases. In this case, where we have a bar over the variable, this is still specific volume, but instead of defining the stuff that we have as pounds mass or as kilograms, here we're dividing by moles. And if we divide by moles, then this becomes the universal gas constant, which will be the same for every gas. But if we're engineers, we're usually talking about more quantity of stuff. So we usually talk about specific volume in terms of pounds mass or kilograms. And in order to do that, we sacrifice the universality of this gas constant. And then we start to talk about a specific gas constant that changes depending on the gas you're talking about. This line says the same thing, that the universal gas constant divided by the molar mass of the gas is equal to this specific gas constant. Either form of this equation is the ideal gas law. We get this ideal gas law when the compressibility factor, capital Z, is equal to 1. So when is capital Z equal to 1? Here we can see on this graph, if pressure is much less than the critical pressure, then all of these curves for different reduced temperatures converge down to a value of 1. You can't exactly see this because this isn't zoomed in very much at the low end, but all of these lines converge to a value of 1 at PR is equal to 0. The other thing that happens here is if our temperature is much higher than the critical temperature. So as we get further away from our vapor dome, then we become closer and closer to this ideal gas law. So when we invoke the ideal gas law, what we're really saying is that Z is equal to 1, or that we're very far away from the vapor dome. Now there's different versions of this equation, and my brother, who's a biochemist, would use this version with the bars and this version with the bars. But in engineering, we're usually talking about mass instead of moles. So we define how much stuff we have by pounds or kilograms. So we're going to use this equation, P times little v is equal to the specific gas constant times T. Or if we want to find the mass, we can say P times big V, or volume, is equal to mass times the specific gas constant times the temperature. So we've already talked a little bit about specific heats, CV, which is partial of U divided by partial of T, and Cp, which is the partial of H divided by the partial of T at constant pressure. We've talked about these a little bit already, and we've shown that if we assume Cp is constant, which it actually isn't, then we can approximate delta U as Cv times delta T and delta H as Cp times delta T. Now, we've said that we can do this for liquids and for solids, but it turns out it's not a terrible assumption for ideal gases as well, keeping in mind that these assumptions get worse as our temperature range gets bigger. So this is more true for small temperature differences and less true for large temperature differences. So if we're trying to find delta U for ideal gases, we have two options. The first is to use delta U is equal to Cv times delta T. Now, it's important to remember that for ideal gases, unlike solids and liquids, Cv and Cp will have different values. So you have to look up the correct value here. So first, we'll look at this option, right? So this first option is assuming constant specific heat. Our second option, we will assume variable specific heat, which will force us to look up values on tables. So here, let's try to find delta U between two states. We look up Cv for air, and in this case, it's 0.733 kilojoules per kilogram Kelvin. So I have air. The temperature goes from 1 bar to 10 bar, and the temperature goes from 293 degrees Kelvin to 564 degrees Kelvin. So, using constant specific heat, I'll just say that delta U is equal to Cv times delta T. I know that Cv is 0.733, and delta T I get just by looking at my table. So here, the units of Cv are kilojoules per kilogram Kelvin. The Kelvin cancel out, and I get that delta U is just under 100 kilojoules per kilogram Kelvin. Now, it's important here, I never actually find out what U2 or U1 is, but the first law really only asks me what the difference is, so that's okay. But this particular assumption is less accurate than if I looked up these values on a thermodynamic table. So we have the option to do that as well, and this option becomes more and more attractive in terms of accuracy as our temperature range gets bigger and bigger. So if I want to find the properties of air, which is an ideal gas, I go to table A22 in my textbook, or A22E if I'm dealing with imperial units. So here, it's a little bit interesting because if it's ideal gas and it's air, I only need one of these properties. So here, if I know temperature, or I know specific enthalpy or specific internal energy, we won't worry about S superscript 0 yet. And PR and VR are reduced pressures and reduced specific volumes. So here, I know for state 1 that my temperature is 293 degrees Kelvin. So that's between 290 and 295. So I can linearly interpolate to find that the specific internal energy in this case is 209.06 kilojoules per kilogram. So if I want to find state 2, I look on my table and I find rows that are close to 564. Again, I'm going to interpolate here, and I'm interpolating for specific internal energy, and I find that U of state 2 is 407.44. Notice in this case, I got actual values for U2 and U1. Now, I can put these into my calculator and find that U2 minus U1 is pretty close to the same value that I used for Cv times delta T. So in this case, my solutions for constant and variable specific heat are pretty close together. But that won't always be the case, particularly as my temperature range gets bigger and bigger. So thank you for joining me on Thermo Shorts. I'll see you next time.